In a simple bridge, you place a length of material across a gap in the ground. This material is usually flat and rectangular. The force acting on the material is gravity, which acts through the centre of mass. The force acts downwards on the bridge. However, the bridge is spanning a gap and is held up at either end by the ground that it sits on. In response to gravity, the ground at either end of the bridge generates a reaction force upwards. So we have a situation where one force acts in the middle, pulling down, and two other forces act at either end, pushing up. Along the edge of the material, two very different situations are established because of these forces. The forces set up a twisting motion on the bridge, making it bow in the middle of its span. The forces on the bridge at the top are under compression. That is to say, that because the bridge is bowing downwards, the materials at the top of the bridge are being squashed. Underneath the bridge, the forces have set up a system where the bow makes the edge of the bridge stretch. The bottom of the bridge is longer than the top of the bridge. Because of these forces, the top of the bridge is in compression and therefore feeling a stress, and the bottom of the bridge is in expansion and feeling a strain. Materials to make a bridge need to be hard. Hard, in materials science, means that if they're exposed to a sudden force, they do not fracture or break apart very easily. The opposite of hard is brittle, where an exposure to a small force results in the shattering of the material. A brittle material is far more likely to cause a fracture in a material. This is where the application of a force causes the bonds between atoms to break apart. One bond breaking apart puts additional strain on another bond nearby, which will break and lead to a cascade of breaking bonds, like the unzipping of a coat. This unzipping is called a fracture, and is only stopped when the breaking of bonds meets a very strong bond that will resist further breaking. Usually, this happens when the fracture meets a series of bonds oriented in a different direction. Annealing a material makes objects harder by adding fractures into them. It may seem to be the case, but when you heat metal and strike it repeatedly with a hammer, you are making it stronger by introducing more fractures to its lattice structure. Adding in many small fractures means that no one fracture will become large enough to cause an overall failure in the material. Rock is a classic example of a hard material. In general, a rock will contain many different crystals of mineral which form a complicated lattice, which will only allow a crack to move a short distance before it is stopped. The problem with types of rock is that they are brittle. They do not work well when exposed to strain rather than stress. If you try to stretch a rock, it will fall apart after a fairly low force, compared to other, more elastic materials, such as refined metals. An ancient solution to this problem of rock was to change the shape of the bridges, or lintels in windows. If you make the stone bridge or lintel curve upwards, opposite to how it would lie naturally, you are placing the underside of the bridge element under compression rather than extension. Now, instead of the bottom of the bridge being stretched outwards because of gravity, the bottom of the bridge is now squashed together because of gravity. The top of the bridge is now in extension, and so susceptible to a strike from below. As this is difficult to achieve, the curved bridge is far superior to the flat bridge. The most modern bridge development has been that of the suspension bridge, which uses a system of materials that is entirely in extension rather than compression, but uses woven, refined metals in cables to hold the forces of the bridge in check, rather than the strength of a brittle rock-based material. The advantage of this is that the bridge can be extremely light for its size, and cost less to build over a greater distance. 1 ton of material built into a suspension bridge could span a far greater gap than 1 ton of material built in a traditional arched bridge.